Dear students, in this lecture, we are going to learn about MC Kulopet's model of neuron. So he was the person who have introduced the model of the neuron. Okay, so he was the person MC Kulopet's. So this was the first neuron model, and it will have only two types of inputs. So remember, one is excitatory and inhibitory. Excitatory waits for positive magnitudes, and inhibitory weights will have the negative magnitude. And the inputs of the Mulopet's neuron is 0 or 1. Okay, so just I'm telling it will have two types of input, excitatory and inhibitory. Excitatory means in order to have the positive weight magnitude, and negative weights will be there for second one. Okay, so here we have to remember that we'll have two types of weights, one is positive and one more is negative, and it will take input either 0 or 1, not other values. So it has a threshold function, so as an activation function, and output signal y out is 1 if the y sum is greater than or equal to 0, else it will be 0. So if threshold are given 0, if it is greater than 0, the y out will be 1, else it will be 0. So that diagrammatic representative. Okay, all of you see here. So we'll have the input signal. I'm giving all the weights x1, x2, whatever the values w1, w2, so on. So this is our summation, and you'll get the y sum. If the input is greater than threshold, you'll y out as 1. If the input, this y sum is less than threshold, we'll get the output as you will take less than 0. So these neurons can be used only for logical operations. So like and or not implication, all these things can be designed with the help of this model. We'll check one example. So for example, we have a John carries umbrella according to these scenarios. So first scenario is it is not raining nor it is sunny. So it is not raining nor it is sunny. It is not raining but it is sunny. It is raining and it is not sunny. It is raining as well as it is sunny. So in which scenario I have to carry the umbrella? So for this, I'll create two things, x1 and x2. So that is our conclusion. I have to get, is it raining or not? Is it raining or is it sunny? So the value, both the scenarios will be either 0 or 1. We can use the value of both weights x1 and x2 as 1 and the threshold function as 1. Okay. So the neural network model will look like, see here. So x1 is 1, is it raining? 1, is it sunny? 1. So according to the inputs, I'll create the y sum and I'll calculate the threshold value. So when I calculate the threshold, these values, so x1 is 0, x2 is 0, y sum is 0, the y out will be 0 according to the summation. 2, it is 0 and 1 according to the summation. If you use 0 into 0, you will get 0 plus 0 is 0, 0 plus 1 is 1. Again, 1 plus 0 is 1 and 1 plus 1 is 2. Okay, so I'm just adding without any weights over here because I'll have x1 and x2. So x1 plus 0 plus these two. If I add these two values, I'm getting 0. Okay, I'm using this value, I'm getting 1. So remember the threshold value is, if I take threshold as 1, if threshold is less than your given value is less than 0, the threshold is 1. So the output will be 0. But in this case, the threshold is sum is 1 and the threshold also 1. So 1 less than or equal to 1, so I got output as 1. So if it is you are getting 0, the sum is 0 according to the threshold, it is less than 1, so you will get the 0 out. So here it is 1, so all these things 1. So here also see 2 is greater than 1. So I'll get here the y out as 1. So this way we can design the similar general MC Kulopet's model. Okay, in order to find the conclusion or result. Yeah, exactly. So this is a thing. So first I calculated weight, then y of sum. My threshold value is 1. So if x is greater than or equal to 1, so this is my threshold here. This is y sum. Y sum will be 1 if threshold 1 is greater than or equal to 1. 0 if less than 1. So same thing we have implemented in this particular table. So these are the two main functions which we will use in order to find the result. So this is the thing. So 0, x1 0, x2 0, y sum according to the threshold I'm designing the network. So accordingly, I'll get the output for these two. Okay, if my x1 is 1, it is raining. x2 is 1, it is sun. So this is the output. Now coming to the next topic is linear separability. So when you get different set of points, okay. So one second. So exactly how I'm going to use the linear separability. Okay, one second. So what is linear separability? Suppose I'll tell you. So suppose I have some values 1, 2, 3, 5. Okay. And I have some other values 2, 3, 6, 7. Okay. Now I have to find the similar elements and what is the separability I can draw between these two values. If I take these two 1, I can take 1, 2, 3. I can say that all these elements are less than 5. Okay. If I take here 5, 6, 7, all these elements are greater than 5. So what is the linear separability? What is the line between these two elements? So 2, 3, 4 over here and 5, 6, 7. 4 is not there. Yeah, 1. So this particular line is called as linear separable. Okay. So you are taking set of elements where you can create one separation between these two. So if you plot elements on a graph, so if a set of points can be separated with one single line, that is called as linear separability. Thus, that thing is called as linear separability. Okay. So one second. Yeah. So we have set of points here, x1 and x2 belongs to one class, all these points. So whenever I'm drawing the graph, if you see here class 1, class 2. So your class 1 orange color is class 1 and class 2 is blue color. Okay, now I can draw a line. In this example, I cannot draw any line because see here, if I draw a line, suppose like this. So again, blue points over here. Suppose if I draw a line here, what I'm getting here, again, orange and blue are combined. So in this example, I cannot separate these values. Okay, I cannot separate these values because these values are not linearly separable. Okay. Suppose if I take another example. Yeah. So there is no, if you see this particular thing, there is no linear function which can separate the class 1 and class 2. Okay. So what I have told just now. Now, suppose if I take another example, all of you see here. Yeah. If you see the same example, another set of points like what we have done x1 and x2. If you take this green particular line, I'm separating this. This is called as hyperplane. So I'm drawing your green color point as a line. So this is in class 1 and this is in class 2. So this particular set of values are called as linearly separable. So whenever you cannot draw any line on the given set of points in order to divide into two classes, those values are not linearly separable. Whenever you can draw one line hyperplane where you can separate the two classes differently, that particular set of points are called as linearly separable. So in this example, using this green color dot hyperplane, we can do. Okay. So here it is the non-linear separable data. Okay. Okay. Now coming to the next one. So what is a summary of this one? If you can separate two set of classes with the help of some hyperplane, those values are linearly separable. If you cannot separate, that are linearly not separable. So that is called as, the concept is called as linear separability. Now coming to the perceptron. So in order to do this particular thing, we should have a classifier called perceptron. So linear classifier will convert particular data labels into different classes with the help of their features, or you can tell that their whatever their performance and how to get those values. Okay, so we can use a perceptron layer, single layer perceptron model in order to use the linear classifier. So you create one single layer perceptron, which will divide the set of points into two classes. Okay. So it will calculate the weight and whatever the required parameters, and it will take the input and it will use the threshold value, and it will say that accordingly it is linearly separable. So if I take here the perceptron example, I have all the inputs. So these are x1, x2, so on, x5. Next to W1, W2, all these are weights. And I'll calculate the summation according to threshold. If the values are less than threshold, okay, suppose if I take threshold as 1, if this output, what I'm getting, the summation, whatever I'm getting, if it is less than 1, these are in class 1. If they are greater than in 1, I can say that these are in class 2. So done. So who is linearly separating these values? This particular threshold function. Okay. So this way I can use one perceptron, single layer perceptron model in order to find the linear separability of the given values. Okay. So exactly. So here we'll have the two-dimensional data set with all the points. We are taking x1, x2, or x1 is greater than x2 belongs to the positive class and x1 is less than x2, it will be negative class. So I'm defining a hyperplane called defined by x1 minus x2 equal to 0. So then we'll create one data set with the 20 points. And what I'm doing, I'm drawing this particular line. If you see here, this line will be drawn with the help of that linear separable perceptron model. And all these values, whatever less than this below the line are positive and above the line are negative. Okay. So by this, we can accomplish the linear separability with the help of perceptron model. Okay, so how we can use, we can create one this model where you can train the data and then we can separate the data. Now, the next concept is Hebb network. So what is meant by Hebb or Hebbanian learning rule, which is an architecture of a large number of interconnected networks. So it will have the connection weights, inputs, and activation functions, and it will just define the rule in order to maintain the network. So whenever this is Hebb network, you'll have all these things. We know soma, dendrites, all these are dendrites. Axon is there. This is your nucleus. And these are Michael sheath, the node of Ranvir, and axon of other terminals. So this is a basic neuron. Now, what is meant by Hebb network? So when an axon of cell A is near enough to excite cell B and repeatedly or permanently takes placing in firing edge, some growth, progress, or metabolic changes takes in place in one or both the cells such that A's efficiency as one of the cells firing B is increased. Okay, so don't worry about the definition. I'll tell you what exactly is going to happen. So what it is here? Okay, I want to go to the previous slide. Yeah. Suppose each, which, one second. So these are the dendrites of each and every neuron. Okay, suppose if you take this is dendrite of another neuron, this is another, this is another. Suppose if I'm taking this neuron as A, okay, and this neuron which is connected here, it was B. Suppose this particular neuron B is in a condition where it is going to excite. Excite means become active. Okay. So when it is becoming active, it is increasing the efficiency of, so it is increasing the efficiency of A. Okay. So because of this particular excitement, the A's efficiency is going to increase. Okay. So this particular concept, okay, if one neuron is exciting with the increasing of the efficiency of another neuron, okay, this can be done only with the help of Hebb network. So this type of network are called Hebb networks. So it is increasing the A's efficiency because of the firing of B. Okay, so if we have two interconnected networks are on, suppose two neurons are in active mode, then the weight associated with these neurons can be increased by the synaptic strength. Okay, so few neurons can be like their efficiency can be increased with the help of the increasing the strength between the two neurons. So this can be calculated with the formula. So ith value of nu Okay, W, ith value of W old plus ith value of X into Y. So here, new weight can be calculated by adding the ith value of X into Y. Okay, suppose if I have A is there and B is there. Suppose the weight of already old one is W. Now I'm calculating the W new. What I'm doing? So W new equal to W plus whatever the wage, and I'm calculating the multiplication of these two values, A into B. So which will increase the strength of your wage. Okay, the synaptic strength. So this is the basic rule of the Hebb network. So because of this one, whose strength is increasing, A neuron efficiency is going to increase because of adding the B's neurons weight. So this is a structure. First, we'll take the start flow chart for your Hebb network, initialize the weights, and for each and every one. So what I'm doing, I'm activating the inputs over here, ith value of S, and I'm getting the outputs. And what I'm doing, new weight I'm adding with the help of this formula. So ith old plus ith value of X into Y. Then finally, what will be the bias will be updated. These two are the Hebb network rules. Bias will be B new equal to B old plus Y. Okay. So this is a basic concept of the Hebb network. So what I'm doing, we are taking all the values, calculating the weight and updating the weight and bias according to the required ith or jth neuron. Okay, so what is the step one? We are initializing all the weights. So here W1, W2, and Wn. So these are the weights. Okay, so here S is the input vector and training output vector. Then what I'm doing, every time this will be a loop. Every time I'm calculating the old weight. So ith value of S for I equal to 1. So I'm using the linear function defined as f of x equal to x for all the x. And what I'm doing here, every time I updating the weight value and the bias value in order to get the efficiency of the neurons. So step 4, it will give the all the output activations. And step 5, I'm calculating the same. I'm calculating this particular thing. So new weight equal to ith value of old plus ith value of X into Y. And new bias equal to old bias with plus 1. So then it will increase the strength of the old new neuron with the help of the firing of the old neuron. Okay. So these are the inputs. So we have X1, X2 and bias, and Y is there, target is the Y. Then training that particular data, if it is, see here, one set on. If both the inputs are one set on, so very simple. But we have -1 instead of 0 because Hebb network uses bipolar data, so we cannot mention any 0. So 1 is there, -1 is off, one set on. Okay. Now, so how I'm calculating here, starting with the step 1. So we get W values are W1 equal to W2 equal to B equal to 0 because weights and bias are initialized to 0. Now, first input X1, X2 and B. Okay, if you go here, X1, X2 and B all are ones. Our target is 1. Now, target is 1. Now, the initial weight of the old weight, how you are applying? New weight equal to old weight plus ith value of X into Y. So W1 new equal to W1 old plus X into Y. Okay, so X1 into Y. So what is old weight? According to this formula, old weight is 0 because W1, W2 equal to 0 plus what is X1 into Y? What is our X1? 1. What is Y? 1. So 1 into 1, it is 1. So your new weight will be 1. Okay, I hope it is clear. So just I'm substituting in the formula. Now W2 new equal to W2 old. What is W2 old? 0. And what is X2 over here? X2 is 1. And what is 1 into 1? 1. Okay, so your weight will be changed. Now bias. Old bias, what was old bias? Okay, B old plus Y. So already according starting we have initialized everything as 0. Now we are adding the new. So new target value is 1. So 0 plus 1 equal to 1. So like this, we will update all the values from starting each and every node. So this will increase the signal strength and also help the to increase the new neuron. Okay. So final weights after presenting all the values. So these are the final weights. Okay. So like this, we have to calculate for everything. Again, same thing. I'll take second input. What was the second input according to the table? Yeah, 1 minus 1, 1 minus 1. So 1 minus 1, 1. So these are the again same values. Again, I'll get the delta weight. What is delta W1? Difference between two values. That is x1, y, x2, y, b equal to 1. Now these bias delta W1, delta W2 and B will be used in this case. Okay, so if you take W1, W2, WB is these values. One second. W1, W2 and B are ones. So these ones will be used in this particular connection. Again, I'll get the values. Again, I'll calculate the delta W1, delta W2 and bias. Then I'll take the third one. Again, these new weights. Again, I'll calculate W1, W2 and B. So this will be repeated for all the values. So what I'll get here, x1, x2, b and y, changed weight, new weight 1, new weight 2 and delta b. Finally, these are the values. So this can be calculated using the Hebb network. So this is the value. This is a final one. Here you have to use this particular values. So you'll have x1, x2, minus 2, 2 and minus 2. When I take minus 2, 2 and minus 2, the output of y is 1. Okay, your targeted y is 1. Done. So in this session, you have learned about the perceptron model, what is Hebb network, and we have seen what are the different applications used in your linear separability and how to separate this one, and what is MC Colopitz model. Okay, thank you.